First of all, thank you all for joining. For those who don't know me, I'm Sundar Vedantham. I'm in Allentown, Pennsylvania. Both myself and Gage Yates from Austin, we both were in an IEEE GlobeCom conference that took place in December in Singapore to present event dev. That's more of a Intel-driven and industrial consortium-driven library that goes into DPDK. Intel was a big patron participant in this IEEE GlobeCom. So there were about 15 plus people from Intel. This is a huge conference where some maybe 2,000 people participated, meaning attended. And amongst the 15 Intel people, there were several keynote addresses, industry panels, workshops, tutorials, and other presentations. Since this is a GlobeCom conference, meaning focused on communication, the focus was pretty much 5G everywhere. And by attending several sessions, reading, learning, I kind of come to realize that there is a lot more to 5G than simple faster speed and more data alone. So I thought within Intel it would be a good idea for us to discuss what 5G is, what the big technological enablers and what the implications to society, etc. So I gave this talk once in Bangalore. It was well received, so I thought I should do it here one more time. I titled the talk as Slicing Implications on 5G Networks because towards the end it talks about slicing and what its implications are. Since we are driving towards that, I named the talk this way. But in the talk, I intend to cover first what is 5G, and then the important technological domains within 5G. When I spoke to different team members, when I asked what they think 5G is, I got different answers. Some said probably just like faster network with more bandwidth. Some thought it's mainly something to do with radio, but it's all that and more. And so for my own understanding, I came up with a way to look at this in 5 big domains where changes are taking place compared to 4G. So we'll talk about that. Then for those domains to progress, there are specific technical enablers that need to come to fruition. They are in progress. They all need to be tied together for the entire ecosystem to work properly. So we'll touch upon that. Then the slicing and its implications to 5G. Right. You can stop and ask me questions anytime. Ask all the tough questions. 5G is so massive that I don't believe anybody would know everything there is to know, but the questions you ask probably would force me to go learn some more and come back to you with the right answers. Right. So to start with, you might have seen a lot of slides like that in any presentation discussions that you've had. 5G is going to be everything smart, everything connected, 5G is coming, etc. So it sounds like there is a lot of marketing hype, but that also brings in a lot of energy. So I was actually pointing out this particular book that you may all have heard about it came out in the 1984 kind of time frame, What They Don't Teach You at Harvard Business School. If you really look at the book, it just talks about people in business need to develop personal relationship and work on their customers nicely and things like that. So if a pure engineers named the book, they would have named it something like Some Useful Management Principles, and nobody would have bought the book because it wouldn't have caught any attention. But making it titled this way attracts a lot of attention and brings in a lot of energy. And at least in case of 5G, I think all the attention is fully deserved. So don't think of it as just marketing hype. I truly believe it as transformational potential, not only to technology, but society on the whole, right? So we'll touch upon that. So 5G plus IoT, that's going to require a lot of changes, and there are a lot of numbers floating around. There are things like this 3.3 zettabyte of global data traffic that's going to flow through by 2021, and then there is $1.4 trillion of spending on IoT alone. Many of these, sometime when you look at it closely, as engineers, we may tend to think, is that really correct? Is it going to come, or where is it going to be in the end? But at least projections, though they may not be very accurate, it's better than not having any at all, because that gives an idea of the kind of scope, where we need to focus, and the energy and so on, right? So coming to what is 5G itself, it's a large umbrella, because it covers everything on the kitchen sink, kind of deal. So I'd like to think of each G as a decade-long setup, build-up, and rollout process. That's what even like many industry experts that I was talking to in these conferences seem to think. So 2G, 3G, 4G, we know we have lived through that. We are in 4G. So you can think of 2G as like the mere cellular communication networks that came in. And the 3G brought in data to cell communication, and then started bringing in apps. And then in 4G, we have much faster data rates. We know all this, but we should notice that in case of 4G, for example, the faster data rates made several applications that wouldn't have been possible in 3G at all, right? So if you think of applications like Uber or Ola, things like that, that would have been possible in 3G. So not only that 4G brings in just faster data rates, but it also enables several applications that wouldn't have been possible in the previous networks, right? And 5G, if there is any indication, it's going to be even more massive. So it's going to be reactive, smart, connecting all kinds of devices. And within Intel itself, we have been constantly talking about autonomous driving cars, and IoT, things like that. And as we walk through these slides, I hope you'll realize that the changes and the improvements that are being brought in would similarly enable not just one or two, but a significantly different and improved set of applications that can potentially transform the society, right? So there is a lot of potential. It does provide higher speed, greater capacity, and lower latency. The lower latency is going to play a significant role in what applications get enabled. We'll talk about that also next. It does distribute the intelligence throughout the network. What we mean by that is, compared to the previous networks where you have the handset and then the actual processing of the data or any information that you need usually comes all the way from back of the network. Now it gets distributed all across. That helps in multiple ways to speed the network up. And it's also going to sort of meld the wireless network, cloud computing, as well as actual computing in various domains, right? Tries to tie them all together and take advantage and leverage each other to deliver a much better user experience, potential, and possibilities. What is Intel doing in these areas? We know we sell chips, but on top of that, we do have a large standards organization. In the GLOCOM Singapore conference, we did have a big presence from the standards group. Asha Keddy, who's one of the VPs, gave one of the keynote addresses. So teams like that are really working on driving the standards development process. Since again, there are so many disparate components that need to work together and come together to make this a reality, making sure that things would interoperate. Different equipments, different radios, different technologies will all work smoothly to make it possible, becomes significantly important. And like tying it all together, developing the standards is not easy, right? So there is a lot of standards related work that goes on in 3GPP, IEEE, organizations of that kind. And from 2016, 17, 18, 19, there are multiple releases that are being planned, being worked on. Just last month, I think there was a big release on one of the standards that came out. You might have seen circuit articles and so forth. So Intel is plugged in, involved in multiple standards development in addition to understanding where the market goes and how we are going to leverage and provide the needed infrastructure components as well. So coming to 5G itself, this is how I'd like to see the big bundles in the domain. When you look at other talks or other presentations, you might see different kinds of classification or maybe people focusing on one area significantly. That's quite okay. I just came up with this framework simply because it helps me think of 5 massive areas where there is significant amount of work going on, and each one of them deserves their own bullet because there is enough energy, enough money, enough thinking that goes into it. First one is the massive MIMO aspect of 5G. So these 5 areas that I am trying to list are the ones that significantly makes 5G different from 4G, right? These things did not exist in 4G at all. So the first one is massive MIMO. We'll dig into it a little bit more, but it basically means the antenna array that's going to be massive in number, and MIMO stands for multiple input, multiple output. And then there is cognitive radio, which means the radio components of the entire 5G network is going to be much more intelligent and sensitive to changing situation parameters so that the available bandwidth, available spectrum, etc., are all put to good use in a very combined, smooth way, so that the end user gets a significantly better user experience compared to where 4G was. So we'll dig into each one of these just a little bit more in the following slides, but I'm just setting it up. The low latency aspect alone, I think, deserves its own bullet because the impact of the low latency in the network is going to have major consequences as to what becomes possible or what new applications can potentially be deployed, right? And it's not easy. In the end, it may be just shrinking the number of milliseconds and microseconds that it takes for the data to come back, but that has major consequences. So I think the amount of work that goes into it to make it a reality deserves its own bullet. Right? Then there is HD, HETNet, which stands for High Density Heterogeneous Network, meaning the network for 5G is not going to be a brand new, simple, uniform one. It needs to be heterogeneous. It needs to interwork with 4G and 5G. It needs to work with cell towers and Wi-Fi and every other kind of equipment signal that's going to be out there. And it also has to be high density, meaning wherever you are, you should not lose signal. And so this HD, HETNet related work that brings in compatibility between different networks. How do you switch from one to the other smoothly? Again, there is a lot of academic work, industry work going into this area. So I listed that as one bullet. The last one is the collaborative computing aspect. We generally think of collaborative computing as maybe 2-3 things coming together to do something. But in this case, there are massive disparate items, equipment, network components that need to interwork, drive towards one end goal to make it a reality. So that there is also enough work going on in this area. So on the whole, I believe most of what you hear about in 5G will probably fit into one of these 5 categories. You might see some talks that combines massive MIMO and cognitive radio as like one bullet because it's all radio related, which is okay. But I just separated them out because there is enough work going on in each one of that. I mean, not like equal amount of work going on in each one of these, so that it's easy for us to understand the significance. So just to touch upon each one of the items we mentioned before, massive MIMO, you might have heard that term before. In case of 4G, you might have seen a lot of cell tower antennas all over the world. Each antennas usually have maybe 4 elements, 6 elements, something like that, right? And the way it works is you take the signal and then you just broadcast it into the ether, hoping that you will reach all the users that are out there, which is okay. That's how it's working currently. But the actual efficiency of the amount of energy used and the actual amount of communication that takes place is actually abysmal. Okay, when I often ask our colleagues what percentage of the energy that's being transmitted from a tower is actually put to good use, right? I mean, think of it like instead of the wireless model, if you have a wired connection, how much power you would need to get the same amount of communication going, right? So if you make some comparison, people usually say, yeah, we know a lot of energy gets wasted, so maybe 95% gets wasted and 5% gets used, something like that. It's actually a lot worse, right? Talking to radio equipment people in these conferences, we've come to realize that it's actually like 1 billionth of the power is what is actually put to real good use, right? It could often be even less than that. Because most of the time the energy that gets transmitted just bounces off of buildings or gets absorbed in flora around, etc., and it doesn't really amount to anything at all. So only a very, very small, minuscule amount of energy actually gets utilized in the 4G communication taking place. So 5G tries to address that in a significant way. So in case of massive MIMO, instead of having 4 or 10, 12 elements, there are attempts to create cell towers that will have 1,000 antenna elements. Okay, so you can imagine them something like this, where there is this whole array of elements that's spread out in all 360 degrees, maybe even at different altitudes. Then the way it's expected to work is if you have an individual handset, when you make a connection, let's say this particular element will start talking to this particular handset, and then it will start what's called beam forming in the industry. So beam forming meaning that the radio frequency gets formed into a beam that's pretty much focused like a laser onto that end user equipment, right? So this can improve the energy utilization significantly. So and as you move from here to there, of course, you will get a handover, and then your same equipment will start talking to the adjacent element. And then as you, let's say, drive around or move, you will quickly move from antenna element to antenna element. And of course, there are, even in 4G, as I said, since a lot of energy gets wasted into the ether, the cellular industry tries to do a lot of things. So for example, when they move from spring to winter in the US Northeast, when all the leaves in the trees fall off, they can actually turn down the amount of energy that need to be transmitted. So they do things like that. So any little advantage that you can get to save power is immediately jumped upon, right? And not only that, it's not only just to save power. If you have way too much power, that's going to actually interfere with adjacent cell towers that may be trying to use the same frequency or trying to communicate with the users in that space. So it's important to use as little power, but adequate power to access all the users in your cell tower area, but still currently it's in a large landscape where most of the power gets wasted. So 5G tries to correct that by bringing in this massive MIMO model. And of course, it's easier said than done. You can imagine as you move around, even now, of course, we do simple things like switching from one cell tower to the next or from cell tower to your home Wi-Fi network. So those handovers do happen. We know how to do them. But here we are talking about doing it in order of magnitude faster in a smoother way, right? So you can imagine this will be like maybe within few meters you need to keep switching from one element to another and keep forming these beams to very narrowly send the signal to that one handset alone, and keep switching it over as the equipment moves around. So there is a lot of PhD level work going on, new models being proposed, how to fine tune the beam forming, how to increase, decrease the energy level. There's been ongoing, a lot of papers being presented. But it's all not in theory level at this point, right? So we saw, I believe Ericsson has a 1024 element antenna that's been prototyped. It's shown to be working properly. So this is coming, right? So this is one huge area. Then comes the cognitive radio aspect. So currently, we all know there are different spectrums that are assigned to 3G, 4G, and so forth. And since 4G has been extremely successful, the bands that are allocated to 4G, particularly in urban area, are extremely heavily used. It's very dense and crowded, right? At the same time, there are a lot of other frequencies that are out there. So, for example, take TV frequencies or frequencies assigned to military that are available but usually underutilized, right? So there is a lot of work going on trying to figure out how to pull those frequencies in to make better use of them under 5G, but without really affecting the functionalities that need to be delivered for TV and military and so forth as well. So the cognitive radio aspect, it brings in software, there's new equipment being defined. So there is this radio environment. Then whenever there is this radio frequency stimuli, it will sense the spectrum where you are, make sure it actually is using the correct one, and or analyze adjacent spectrum, then do spectrum analysis to see is this the right one, or are there adjacent spectrum that are freely available, assess channel capacity, then go back to radio environment to maybe switch you over to adjacent spectrum, right? And while doing all this simultaneously, let's say if a military equipment or some communication need to take place, that also should be given priority over 5G, right? So the best effort aspect is also being thrown in. So you can imagine how complex this can quickly become. But there is enough work going on trying to figure out like unlicensed spectrum where we can use it in smaller domains without interfering with anybody else, and maybe licensed spectrums that bigger towers can utilize and switch between. And there are spectrum broker modules that are being developed that can like negotiate sort of what spectrum is allowed for which users in which equipment, sort of thing, and being able to switch back and forth. And then there is the software defined radio itself that's being built into handsets as well as the cell towers and other transmitting stations. So the 5G handsets that you will have, similar to the cell tower, that will also have multiple antennas within one cell phone, right? So it can communicate in multiple frequencies and can switch back and forth. And there are really some very neat things being done. You all may remember from basic electrical engineering classes that the length of the antenna element need to be roughly like 1/4 of the wavelength. So if you are working on, let's say, two different wavelength, one requiring a really large, long antenna, then another one really requiring a small one. Now there are fractal ideas being used, where you take, let's say, a 1 meter long wire and then fold it 4 times to make it 1/4 the length. Then the thicker multi-folded wire would serve as a single element, like 1/4 the meter, or even much smaller, right? Maybe a 10 centimeter thick piece that will function in one frequency, while the complete wire would work as an antenna for a different frequency. So you can kind of pack multiple antenna and frequency communication capabilities into a single handset. Things like that are being worked out. There's a lot of work going on in the cognitive radio and making sure all these spectrum hopping still doesn't erode the quality of the end signal that the customer would experience. So this is to show, so you may have like a massive antenna here. From here, let's say there is a device here that's trying to talk to the network, but there are some knolls or hills or some buildings that can really deteriorate the signal quality. So there are easy switchover plans being worked on, so where this massive antenna array will actually transmit it to this home Wi-Fi router or some small box that's mounted on this house. Then from there you can get a Wi-Fi signal over to a handset or a laptop that are around, right? So this requires, I mean, this will be transmitted in one frequency, this will be on another frequency, and all these frequency hopping and spectrum hopping should still work very smoothly without any interruption to the call, while simultaneously making sure the latency numbers are also met, right? So each one of this, you can imagine how complex this might tend to be, but enough energy, effort is being put on. This slide just shows the different frequency bands that are in use. So for example, in USA, there is a C band that's in use. In Europe and APAC, there are different bands in use. But now the goal is to sort of meld all this into one big area where 5G can quickly swap back and forth to provide the best possible user experience to the end user, and also simultaneously optimize things like, let's say you need to download a big movie or download a lot of data in one particular handset, right? If you are driving in a car, so depending upon where you are, as you are driving through an urban area where there may be these high frequency bands available that may not travel too far because it takes too much energy. The high frequency bands may be used in the urban area where they are available to help the handset download a lot of information quickly, right? And so I saw some video, some demo showing up to 1 gig per second download speeds being demonstrated in using things like millimeter waves. We'll talk about that in a second. So as you drive through a building where there is this high frequency link available, you'll download a lot of information. And then as you drive off, you may switch to a different lower frequency that may provide you reliable communication, but it doesn't have enough bandwidth to send you a lot of information. So the handset would kind of adjust itself to buffer up the information and then use it later. So think of even watching like a Netflix movie or something, right? So when you are on a high frequency area, you can download a lot of information and then watching it later when there is not a high speed connection to continue the process.
Sundar, you might have covered this already, but these massive antennas you're talking about,
yes,
are they, how do they have to be widespread? I mean, how far away can they travel? Things like that.
Good question. Actually, it comes up next on that HD net, Jay. The simple answer is these massive antennas are mainly for large cell towers, but 5G is going to be a mix of everything, right? So there is going to be even femto kind of cells, smaller one, some drone-based single piece that just flying around, giving you connection, things of that nature that are coming up as part of that HD net aspect. So it's going to be a mix, and everything has to somehow work together. So there are plans to put little cells on each one of the street lamps in the whole city, right? So as you walk from one cell tower, one lamp post to the next, you are technically switching from one cell tower to the next. And of course, in those cases, you are not going to put a massive antenna there. It's going to be much smaller because the density compensates for what the MIMO antennas on the cell tower need to do. But the handset is going to have MIMO as well. So that is going to help you switch from the huge cell tower frequency antenna element to a smaller lamppost based tower that has maybe only one or two elements that will talk to you directly at a much lower power.
Okay, I see.
Did anybody mention kind of effects on the human body of all these waves, and as it gets more pervasive, that we need to be more concerned about that?
There is particularly a lab in Europe. So they are specifically doing experiments of this kind to see not only like compatibility, the Plugfest kind of thing, but also how will it affect human tissue or animals, or what's the effect going to be on the flora and fauna all over the world, things like that. There was one person in another conference in November. I was in Berlin presenting similar stuff. So we did talk about that, and at least he didn't raise any flags at this time saying, yeah, there are dangers that we need to be immediately aware and stop doing this or something. But at least there is the notion is in the whole ecosystem's consciousness. So that's it. It is being tested, as far as I know, more on the Europe side than on the US side. So in the collaborative computing aspect, again, we should really think of how many different elements are going to come into collaborative computing, right? So if simply take autonomous driving that Intel has been really working on. So it's going to get like GPS signal and then drive around. So that's one aspect of computation. But there is this notion of platooning, where maybe 5 to 10 cars, trucks will all kind of electronically become a train, meaning there is no physical connection, but they will maintain just like 10 feet distance and then drive all together like a train with different compartments in it. As they do, there are significant advantages that could be gained, because at higher speeds, you might even gain aerodynamic advantages. Each one of the vehicle is not facing the wind the same amount, and so the fuel efficiency increases. But they all need to talk to each other so they don't run into each other. So they all will be transmitting their position, how far away they are, etc. In addition to that, there are things like each lamppost transmitting some information, stop signs, and anything and everything. So there is within like self-driving car aspect alone, there are at least like 5-6 different things that we can talk about that the car itself needs to do, and it also need to talk to adjacent entities, so that the whole thing can come together and work together properly, right? So this collaborative computing, how much we have to go and what things need to work together for all these things to come together. And not only that, it's also this 5G, 4G things need to work without any issues between them, right? So you can't say this is all designed just for 5G, so it won't work with 4G or anything like that, because half the world is still going to be 4G for a long time. So 4G, 5G interoperability, 5G Wi-Fi interoperability, different device interoperability, IoT, all this need to sort of work smoothly. And technological challenges that are there for research opportunities, etc., are all like phenomenal, right? So there is huge work going on in collaborative computing aspects as well. Then this high density heterogeneous network that I mentioned. So like what we were talking before, you can see this is not going to be like rip out everything that's out there and then just build a new network, right? If you can do that, quite often it would be much more efficient, but it's cost prohibitive. So that's not going to work. So how are we going to do that? Is by somehow making them all interwork. So it's not only the 4G brownfield, meaning well-developed network that need to interwork with 5G. There can also be green fields where there is no network at all, and then we are going there and building brand new networks, maybe in remote locations or countries, things like that. I mean, there were talk about things like in UK, there are companies that just specialize setting up networks for rock music concerts that take place in remote cow pastures just over weekends, right? So they'll go set up the network on a Friday. The music concert would take place Saturday, Sunday. Then Monday they dismantle everything and then drive away. So that's like a clean greenfield situation because there is no network there before. So the company that's specializing in that, they have like racks and racks of equipment that are pre-designed to work this way. So they can go set up a truck, put a couple of racks there, and then they get a satellite link up. And then they start planting a few small towers here and there. So that provides cell phone communication for whatever 2,000 people who are going to show up for that rock music concert for those 2 days. So they'll have cell tower connection, they'll have data connectivity and so forth. And even the television stations can really transmit hi-fi, I mean high def video of the concert to their television stations. But come Monday, it's all ripped apart and everything is taken out, right? So there is nothing left. So there are situations where there is going to be clear greenfield situations, but most of it also is also going to be brownfield where you have large amount of 4G network already in place, and then the 5G need to somehow interwork with that and then slowly replace it over time. So this heterogeneity of the network is very important. And on top of that, it has to be high density because if there is if the density is low, that means you are going to have large towers at distant places. That means you cannot use high frequency spectrums that efficiently because the power of the transmission kind of deteriorates at like the square of the distance kind of thing, right? So you cannot have like one cell tower that's transmitting for the whole city at a very high frequency to provide all the data bandwidth that you need. So the only alternative is to go with a high density network where you can think of every lamppost becoming a small tower and somehow making it all work smoothly going from one to the next. And that also reduces the amount of power that you need because the devices are really close by, and that allows you to use higher frequency spectrum that can potentially transmit a lot more information than what lower frequency spectrums can transmit, right? So it all has to somehow come together. So many of these that we are talking about, it's all actually being prototyped and tested. So I have a couple of 1-minute videos that I'd like to show that just try this. If the video doesn't play very well, I'll send you these links and you can look at this later, right? So this one is Nokia video. So there is a lot of work being done on developing drone-based base stations. So we can attach a base station to the drone, either for deployment or for actually running it. So this particular video shows one of Nokia Bell Labs drone-based station that's getting deployed. The video may be choppy on the remote sites. If so, I'll send that to you later. But as it plays, I'll probably talk through it as well. Right? Let me know if it's playing smoothly.
Can see it, but kind of slow frame rate.
Slow? Okay. To get the gist of the idea, that's good enough. What's really cool is that we saw videos of the prototype actually being designed. You can see the base station unit itself is really small, but the outside is all solar panels, right? So it can quickly pick up the power needed to run that. So that's a case of where an actual base station gets deployed and then the drone goes away, right? So this is another case where the drone itself is running the base station and it uses an Intel device.
So Sundar, it won't be good if there's a northeasters, that day, yeah? If there's a storm that day, that won't be good.
Yeah, there is no audio.
Yeah, Sundar, we can't hear any audio on the
You
YouTube.
can't hear any audio? Okay, yeah, so I'll just talk through that. So basically, they have a functional working base station on that drone, and he was using a cell phone to. So he was actually making phone calls using a real cell phone, using the drone-based base station, right? So it works, and it's so small. So I was also trying to understand, I mean, what kind of power range are we talking about? And all this is like all over the map, right? So there is no one simple answer. So a huge cell tower may run power in like kilowatts. This particular kind of drone-based stations actually use 250 milliwatt, right? 1/4 of a watt. And if it's so weak, you would wonder how far it can go. And they've shown that it can actually cover about 2 kilometers kind of range. So you can potentially just fly the drone above, say, a disaster area where the cell towers are down, and you can quickly get connectivity going, right? So often things that may sound like very science fiction-y, it has very quick real-world application. We can talk about all this, say the California mudslides that's been happening, or forest fire, or earthquakes, and or even like war fronts, any kind of disaster area, right? These help deploy the required base station capacity in that area very, very quickly. And there are also ideas like, let's say you have a massive regular base station that's still up and running, but maybe 10 kilometers down the line, there is a small town that's affected, it has some disaster. Then you can deploy a flying base station above that tower, I mean, above that town, and then shoot your signal from the cell tower that's 10 kilometers away into that one flying drone alone, right? So since it's at a higher elevation, it's easier to establish connectivity maybe at a different frequency, more reliably. So then that drone can provide connectivity to the area right below that drone, right? And there are a lot of work again going on in this area where, for example, if you use a drone, naturally there is a lot of flexibility. You can quickly, you don't need like a runway or anything. You can quickly lift off, go, fly wherever you want. On the other hand, it's going to require a lot of power. Drone is going to run out of power quickly. So there are alternate options like some sort of a glider or a fixed wing aircraft that would require a runway to take off, small ones. But then it can kind of float around for much longer time than a drone. Then there are these Loon, Loon project that Google is running that you might have heard about. It stands for balloon. So basically it's a lighter than air device. So it's a balloon to which a base station is attached. So they can quickly lift it up and let it stay at some elevation. So all the area beneath that balloon can get 5G connectivity, right? Of course, right now they are doing 3G, 4G, but the same thing can be used for 5G also. In addition to disaster recovery kind of situation, there are a lot of additional use cases that I'm learning about. So this rock music concert that we talked about could be one use case. There is no point setting up a massive antenna tower in that cow pasture because once the concert is over, there is going to be nobody there, right? So it doesn't justify the capex in that case. But even in case of, I was talking to a researcher from, an academic researcher from Italy. He was saying in their own university, during the fall registration time, right, there is suddenly like thousands of students that flow in and they all kind of congregate and try to do course registration, etc. in one area. And now that cell phone is pretty common, everybody wants good cell signal in that area wherever that building is. And very interestingly, the drone models work as an exact complement to standard cell tower model, right? Since the cell towers are anchored on the ground, the ideal load distribution, meaning how the user should be spread, is actually in an equal density around the cell tower, right? So that's the ideal scenario where people can make maximum use of the cell tower. But if you look at any of these cases, a university where students are coming in on day one of the semester to register, or a rock music concert, anything, they are all going to be clustered in one physical location, right? They are not going to be spread around. They are going to be in one cluster. And that is probably the worst scenario for a cell tower, because even if there is a cell tower, only one part of the cell tower signal is going to be used, whereas the whatever 270 degree, the other three quadrant cell tower signal is not going to be used very well. But compared to that, imagine a drone-based cell tower which is just flying above that crowd, right? In that case, it actually is a perfect fit because it's going to cover sort of like a circular area in a cluster, right? And signal strength is going to weaken as you radially move away from the center of that circle. And in these cases, that is how people are. I mean, they are going to be clustering around one center around that. So these flying base stations can potentially complement existing standard base station in a very nice way, right? So it can really be helpful, not only in disaster, but in even predictable situation, be it a big game in a stadium where you need to provide a lot of coverage, things like that. So it can really work well. And as soon as it's over, within minutes, you can physically redeploy the same base station elsewhere. So it becomes very convenient. Right, so you should touch upon all the different technologies that are enabling 5G. We have talked about many of these, but just wanted to differentiate what we are talking about, the big domains, the 5 domains that we talked about. Those are areas that differentiate 5G from 4G, but there are lot of smaller level technologies that are coming in that's going to make those domain changes possible, right? So the antenna technology change is one thing that we already spoke about. So as I said, there is like 1024 element massive MIMO prototypes are currently being tested that we talked about. That's already ongoing and getting consensus. Imagine this is again across the globe, right? So there can always be some nation saying, oh, in our country, we don't want that spectrum used for this usage sort of thing, or our military spectrum cannot be used for civilian communication. So establishing standards is really important for equipment to work across the globe. So there's a lot of effort being put in. Then you will hear about millimeter waves. So currently, if you look at the spectrums that are being used, it's in the 3, 4, 6 gig range for 4G. Whereas we are hoping to appropriate much higher spectrum range in the 5G from, let's say, 30 gigahertz to 300 gigahertz. That's called millimeter wave. Since the frequency is 10 to 100 times more, right? So that gives you the capacity to deliver a lot more data. You have a lot of area to deliver data, right? So within those frequencies. So that's very efficient, very good for transmitting large amount of information. But naturally, those spectrums being really high, you need a lot of energy to make transmission, and the signal dies off very quickly. The signal quality deteriorates as you travel along, right? It's not very good for large scale transmission. So I saw some demos of millimeter wave transmitters being set up in a building, and a car driving by being able to get like 1 gigabit per second kind of connectivity reliably. But as you drive away, the signal quickly deteriorates, and so you should be able to switch back to other kind of frequencies that are available out there. So you should like make best use of the millimeter wave when possible to get a lot of data, and then switch back to normal frequencies for larger distances, right? So that 5G NR, NR stands for new radio. So that's the cognitive radio part. There is a lot of work that's going on, again, to stitch it all together, to do spectrum hopping, to make best use of the handsets capacity, the transmitters capacity, etc. together, right? Movable base station, we talked about that. Then MEC, that's mobile edge computing. That is a big area to bring down latency. So you might have heard about that. The idea there is mainly to bring as many elements of the mobile computing closer to the edge where the handset is. The SDN NFV, software-defined networking and network functional virtualization, that's going to enable that MEC ideas, right? So previously, you can imagine, let's say you are doing some data transfer. It might have to go through a firewall, encryption, decryption. All those things were done deep in the back of the network using hardware. And so you need to send all that data through the network to the backhaul, to the data center, where it gets decrypted, where it's checked against firewall, and so forth. But now with SDN NFV, I keep thinking of this more like if you have, let's say, 1,000 Xeon processors, don't think of it as 1,000 Xeon processors, right? So it's become one big blob, like a bread dough. And then you can peel off whatever number of processors you want. Maybe you want 3.5 processors to run a firewall, and then 2.3 processors to run a decryption engine. So you can like peel off that much of dough and then create a network functional virtualization instantiation close to the cell tower. So you can actually do the decryption, you can do the firewall check in the cell tower itself, or wherever you want in close to the edge of the network, and that would significantly improve the latency numbers, right? So you don't need to go all the way back and then come back. So that's going to become possible only because of SDN and NFV, and hopefully Intel will sell a lot of chips in that realm. So that URLLC stands for Ultra Reliable Low Latency Communication. So there are a lot of new apps coming up that are going to be dependent on this ultra reliability and low latency. So one big ticket item that's constantly being discussed is not only the autonomous self-driving vehicle, but also doing robotic remote surgery, right? So there's actually in US, there's a company called Da Vinci that's creating robotic surgery equipment. So the surgeon could actually be in a different city further away, and he or she does the surgery through a haptic network. So the Da Vinci system is located in a different city where the patient is. So the robot will actually perform the surgery, but the surgeon in the other city would actually get the haptic feel as he cuts through a muscle or as she cuts through whatever, a bone, something, then the actual feel, how he or she will feel, the surgeon will feel, is actually relayed back to the surgeon in a simulated way, right? And that requires naturally ultra reliable communication. You don't want like after 2 seconds losing connectivity, and then extremely low latency communication, right? The latency requirements for 5G is 1 millisecond, right? That's how fast the response is expected to be. So just for my own understanding, I ran my phone in different networks to see what kind of latency I get. So currently I get something like 172 milliseconds, give or take some, but you can see it's like more than 100 times worse, right? Whereas 5G is pushing for 1 millisecond. And if that 1 millisecond has to be a reality, naturally it has to get a lot of computation moved to the edge of the network. So you are not waiting for the information to travel all the way back to the network and come back. But once you make that a reality and also make the network ultra reliable, then things like this remote robotic surgery can come into a reality, right? It's currently being done, but on like completely private total networks here and there. And again, it may sound like science fiction. Why do you want to do that? Why can't the surgeon go there, right? But you can quickly see maybe there is a small town that's physically cut off due to a natural disaster. If there is a robotic equipment, the surgeon in an adjacent city can still perform emergency surgery, or even in like a war-torn area, things like that, where the surgeon may not be able to travel. If there is a remote connectivity that's reliable, then a lot of things could be done. Then you will hear about this EMBB, that's Enhanced Mobile Baseband Communication, and then MMTC, which stands for Massive Machine Type Communication. So there is also a lot of work being done in automating industrial manufacturing, right? So very high precision machining, things like that, that could be done with one central controller further away. So because of that, again, it has to have like 1 millisecond latency, so that the machine at the far end actually performing the work will not go too far away without the controlling equipment sitting in a different location, knowing where it is, right? So even if there is like few milliseconds delay, that can end up, let's say, running a milling machine or some cutting something that can go too far without the controlling equipment understanding where it is. So that ultra reliability and low latency both become really important. And if we can achieve that, then a lot more things become possible as well. Right? And all this is related to machine communication, where it could be self-driving cars, or it could be robots performing some manufacturing work, or it could be the remote surgery kind of situation also. And in remote surgery cases that I was talking to people, There are even notions like, let's say the surgeon is fairly old, so he or she may have shivering hands, right? And since the actual surgery is performed by a robot at a remote location, it's very easy to program it to sort of cut out any shivers that's coming from the physical limitations of the surgeon himself or herself. So there could be a lot of good things that will actually make the surgery even better than a physical human being doing it. But for it to work, you also need to have this UR LLC application capacity. So this slide is to show that, yeah, so earlier this is the app's core of the network, and we had the actual end user devices sitting here, maybe industry, maybe home, maybe car, maybe games, whatever, right? And virtual reality, all that. So for many of these ultra reliability and low latency becomes really important. So even imagine a VR situation. So we are saying 1 millisecond delay. Human beings cannot really perceive 1 millisecond that very well. So you can actually increase that number a little bit more. But let's say if you go beyond 100 millisecond, right? I said in the current 4G networks, when I tested, I was getting 172 milliseconds. So beyond 100 milliseconds, if you are trying to do VR, you are going to feel seasick. You are going to turn your head and the picture is going to move slowly enough that it's going to make you sick. So it really won't work. So for it to be really reliable for VR type application, the acceptable number is in the 10 millisecond range, so that it's like within the perception range of human beings, right? For those things to happen, we do want to move some of these functionality in a mobile edge computing server, so that brings in proximity, ultra low latency, high bandwidth, real-time access to network information, as well as location awareness. All that becomes possible if you can move it closer and closer to the end user equipment. So from Intel point of view, we are of course playing in all these areas, right? So you can see all these ideas sort of coming together. So smart devices, of course, we are in autonomous driving, and we are in IoT. We are trying to work with equipment vendors and so forth. We talked about millimeter wave. So basically think of 30 to 300 gigahertz frequency range. High frequency means higher bandwidth, but higher power needed to transmit, and so not carry the signal too long, right, in that combination. But it has to interwork with LTE, Wi-Fi, IoT, all that, the radio access technology. That Eagle Crest kind of devices will probably come into help here. An access and edge network, we are in that. Of course, we are in core network with NFV, SDN kind of thing, trying to help move things closer to the network, and on the cloud side also. So the idea is to basically move as much computing as possible closer to the end user, so that we can bring in reliability plus low latency. Right. So yeah, this is all sounds fantastic and great, but is it all going to be easily deployed? And probably it's not that easy. So the number one issue that I see is nobody wants to pay for it, right? Including myself. If my phone company is coming in to say, instead of $40, I need to pay $80 per month, I'm going to look for somebody else who will give me cheaper deal. So this spans all the way from like the end user to the various companies that wants to benefit from that also. It's part of our own the success is the reason. Intel, we have like done the Moore's law. We've trained the whole world to expect double capacity, power, all that for the same price year over year, right? And so nobody wants to really pay for it. So just for comparison, I wanted you to think of big pharma, right? I've talked to my friends who work in the pharmaceutical industry. I know it's not the same, but I think still there is a lot of value in just kind of understanding where we stand. So hepatitis C is a viral infection that happens to people. A lot of people have it. The negative effect of that is eventually one's liver may fail. That the only recourse at that point is a liver replacement that can cost you whatever $250,000, right, in US. So for a long time there was no real solution to this problem, and then now there are drugs available that can actually cure hepatitis C pretty much completely and without a real surgery or any major MRI or this and that, right? That's simply using pills. So you just take a pill, one pill a day for 12 weeks, then hepatitis C infection goes away, right? So this is available now, but you know what the price of the treatment is? Imagine, I mean, nobody is doing any surgery. There is nothing needed. You just need to take a pill, right? The cost of this treatment per person is about $84,000. Okay, um, per person. So when I was quoting this number or telling this, just wanted to make sure I'm right. I'm not saying it incorrectly. So you can go check it out. The treatment cost actually 84 probably is on the low end. It's for a 12-week regimen, right? So you just take one pill a day. So there are multiple ones. This Harvoni is the one that came in really. Their argument is if you really end up with a liver failure, that takes $250,000. So compared to that, we are giving you a bargain, right? And they have made statements, things like, yeah, I mean, this may have a lot of public pushback, but we don't care, and we are bringing in good value, so we deserve this money, right? And they also argue that it's based on the perceived value that they bring in, not the cost of manufacturing the pill. That's acceptable, but imagine the perceived value that 5G is bringing in, right? But in no way we can go and ask anybody to pay whatever thousands of dollars for the kind of services and the miraculous things that we can bring in. So what is the solution, right? I mean, how are we going to make this a reality? And not only that, it's not a simple one technology upgrade, right? We are not talking about just changing the equipment on existing cell towers and voila, we have 5G. It's not like that. So there are even more stumbling blocks. So how do we solve these issues first? And that's kind of where this slicing comes into play. So slicing, what it means is in the existing network, we basically create slices horizontally. So there is a network functional slice number 1, that's for wireless baseband. Then there is slice 2, that's for real-time use cases, example, industrial control. And then a slice 3, which is for IoT sensor and massive machine type communication. Slice 4 for mobile edge cloud caching, whatever, right? So horizontally you create slice after slice. This may initially sound like just QoS support. In a way it is, but in reality it's not. In case of QoS support, our devices can differentiate between, let's say, VoIP and somebody just reading email, and then prioritize the VoIP call so that the call quality is better. We can do that, but this is going one step further by actually slicing the network so that the higher priority traffic will always get through at a much reliable, low latency, higher bandwidth way compared to the lower priority one, right? So it is to transform this network into this model that can basically help the service provider leverage existing network to derive more revenue out of it. So, I mean, actually think of this. So, I wanted to talk about what the speed of light itself coming into play, basically in this respect, right? Since it's all electromagnetic signal, it's all traveling at the speed of light. And in 5G, we said 1 millisecond latency for manufacturing application. So keep that in your mind. The speed of light is 300K kilometers per second. And so in 1 millisecond, you can expect something like 300 kilometers distance being traveled by light. And we said for remote surgery kind of application through haptic net, meaning the robot remotely does the surgery, and when you cut through the tissue, the feel of cutting through the tissue is conveyed back to the surgeon at a different location, right? So the surgeon is not sensitive at the 1 millisecond level, so you can allow up to 5 millisecond latency for remote surgery type haptic network. So since the speed of light is 300,000 kilometers per second, it's 300 kilometers per millisecond. So since for the latency to work, it has to be a round trip delay. That means you will get only 150 kilometers radius, right? If you go beyond that, it's going to go far away, and you can't keep up that 1 millisecond latency. So if you actually basically lower the limit and then say up to 5 millisecond, it's okay, then you get up to 750 kilometers or about 466 miles radius, right? Which means a surgeon can physically be about 400 miles away and perform the surgery without any like significant delay. That's possible, right? But for this to work, the network cannot be a simple best effort kind of network. It has to be a very reliable network where the path through which the signal will travel is always preset. You can't say once it will go through ABC and then for the next time it will go AC, I mean AZ, Z something, and then come here, because the latencies may change. So you want to be able to find the shortest path and stick to it, and always ensure that your signal that requires these kinds of low latency and ultra reliable communication will always traverse through those nodes to reach the other end, come back at the fastest speed possible, right? And as I said, for virtual reality type communication, the limits are in the 10 millisecond range. So if you go to 50, 60, 100 millisecond, then you are going to feel kind of dizzy looking through that. So for that to become reality, again, very stringent 10 millisecond limit. So this is what sort of kind of pushed me to evolve and rethink the net neutrality ideas, right? So if we are strictly sticking to net neutrality, that is going to impede some of these ultra reliable low latency communication apps. I'm still not like completely like gone through a religious conversion saying net neutrality is not needed. Till like a couple of months back, I always thought, yeah, if the high-end companies pay the service providers and hijack the bandwidth, new companies that come in may not able to have good access to the network. And so I understand all the reasons why we do need net neutrality and the virtues of net neutrality. But I do see an area where it's actually, it might impede some of the URLLC applications coming into fruition. So as a society, people need to think through. So the solution could be sort of isolated networks for these kind of application, or it could be private networks. And of course, if you make networks too segmented and private, it may not work later. I mean, it may not interoperate reliably, and it may also increase costs, right? The reason internet and network, all that is so cheap, is everything is commoditized and it's all standardized. If you take that away, things may work, but it may become more expensive. So, of course, elimination of net neutrality is one reason. Some experts I spoke to in some conference discussions, I did stand up and ask about network slicing. Yeah, it sounds fantastic and that can bring in something, but then what about net neutrality? How are we going to ensure that everybody has access to the network? And the speakers didn't have very clear answers, and actually they didn't want to get into some policy discussion because it's more of a technical discussion. which I understand. But one idea that did come across is with 5G kind of network, the available bandwidth is going to be increased so much that a simple, like a flower shop starting a website that will not become accessible. Some people think it's probably not a real cause for concern. In just accessing a website, that may not become such a big deal. It will always work, and as long as governments and the societies ensure that there is healthy competition between service providers, people will switch to another service providers who provide access to those sites that are not accessible from somebody else, right? So ensuring competition and opening up enough bandwidth might automatically solve this problem and make it not an issue is one argument I heard. I don't know what the correct answer is, but one thing I can see is if you really say somebody watching movie on the web should be given exactly the same kind of treatment as URLLC applications traffic that's flowing through, it may not work that very well, right? Maybe we'll have abundant bandwidth where it's not an issue at all, maybe. If not, then that can impede some of these application development. So it's something worthy of thinking. So that's where network slicing comes in. So if you are using the available spectrum much more efficiently, you actually need less spectrum, and the spectrum sharing can effectively increase the amount of money that the service providers can actually derive, right, from the existing setup itself. So since none of us want to pay for it, it's important to embrace such ideas where the service providers can derive extra revenue. That's also equally important, right? So continuing the major stumbling block, just a couple more to talk about. The greenfield, brownfield issue is going to be one, meaning there are countries, areas, geographic location where there is a lot of existing equipment that needs to work, and then 5G deployment comes in, that's going to change a lot of things. And so everything interworking could be one of the stumbling blocks, right? Then many deployments and use cases will require societal acceptance, right? I've been looking at, for example, take self-driving cars, and how is it going to affect the overall civilization's fuel consumption, right? Studies are all over the place. So I've seen studies that say the fuel requirement can drop by 80-90% because they presume all cars will be electric, and they'll exactly drive in the most efficient way where it's needed and so forth. And then there are projections that says the actual fuel consumption will double. Why will it double? That's because currently we have human fatigue factors like that limits how much we can drive, right? And if cars are self-driving, those limits will all be removed. So cars may be driven a lot more. And in addition to that, there are cases that are like potential situations where, let's say in cities like New York, the parking charge is like $50, and you are going to be in a meeting for 2 hours. At that time, instead of parking and paying $50, you can tell your car to just keep driving around in circles and then come back and pick you up because that's going to cost you only $25. People will definitely do that, and so that can potentially increase fuel utilization also, right? And there are also a lot of other changes that would come in. If you generally look at gas stations in US, they don't make a lot of money simply by selling gas. They make most of their profit simply by selling chips and Coke and other convenience items people buy when they stop for gas. And if you have self-driving cars that stops and fills and moves on its own, not only that gas stations are going to go away because it's going to be more efficient and it's going to stop only in correct places, but cars are not going to buy chips and Coke all the time, right? So that's going to come down as well because people may be just sleeping in the car as it traverses across the country. So that's going to eliminate a lot of second order, third order jobs and situations, and it's also not possible to expect those people to quickly get retrained in Java programming and go work for Google either. So I think probably people like us who will benefit from all these rollouts would probably feel we deserve all the money, wealth, credit that we get. But I keep wondering about the societal impacts also. Hopefully, we'll all look through and make the right decision, talk to the people that we interact with, and so on. Then there are a lot of ethical concerns that also need to be sorted out. So this is my last slide. So you all might be aware of this ethics thought experiment problem that's been posed in the 70s. So here there is a trolley. It's like a train that's coming in. It doesn't have a driver. Somehow it got unmoved and it just flying through these tracks, right? It's coming down. And then there are 5 workers working on this track. For some reason, imagine they can't either see this train coming in, or maybe it's in a curve, something. So if nothing is done, this train is going to come down and kill all these 5 people, right? And then you are actually standing here and you have a lever. And if you just throw this lever, it's going to change the track of the train into this. And so that the train will flow through this track. And there is one other guy working on this track, and so it's going to kill him. So this question is posed to people all over the world, asking, will you pull the lever or will you not pull the lever? And like 90% of the people, irrespective of whether they are rich or poor, young or old, religious or not religious, or what language they speak, they all say they'll pull the lever because it's good to save like 5 lives and sacrificing one instead of letting 5 people die. So it looks like an easy decision, right? Then the problem is restated as, okay, let's say that's not the case. You don't have a lever. You are actually standing here, and there is another guy standing next to you. So you realized what's going on. So you can push this guy down into the track. The train will come hit him. It will kill him, and that will stop the train, and that will save these 5 people. Will you push this guy, right? Pretty much everybody changes their stance and they say no, they won't push the guy. And many of them can't really explain why, because logically you are killing this guy or this guy to save these 5 people. But ethics and philosophers have looked at it and said, basically in this scenario, this particular guy has got nothing to do with this train or the track or the accident scenario at all. And only when you push him into it, he gets mixed up in the picture. So you are the one unnecessarily getting him into the picture. So that poses a ethical concern in people's mind, right? Why am I telling you this on a 5G talk? Is because in self-driving cars, this becomes a reality, right? So far, when you are driving a car, if you are going to hit 5 people, you may decide you want to quickly turn around and go hit this one guy. That may be safe, may not be safe. Your reflexes and instincts may work fast enough or may not work fast enough. So it becomes the individual's decision. But now in a self-driving car, the software is going to make that decision, and it's fast enough. It can always make the same decision all the time, right? So if you're driving and you're going to hit 5 people unexpectedly, should the software turn around and go to the walkway where there is one guy sitting there? Should he be killed to save these 5 people? Yes or no? And it can actually become even a simpler question. You are driving and there is only one person there, and if the car is just allowed, it's going to go hit that person, and it will save the driver because the driver doesn't have any big impact, right? But if the software notices that and then it can put a sudden brake, it will save that person, but the driver is going to lose his front teeth because he's going to go hit the front of the car, right? So does the car company loyalty fall to their customer who owns the car, and so it will not brake the car fast enough and sacrifice the pedestrian, or should it actually let the driver lose 2 teeth and so that the person on the road can be saved, right? So those questions become a reality in these situations, and there are people writing articles saying why should a software engineer in like Austin or Bangalore decide what should happen in a Germany road, right? So all these things will come in. We need to really think through. Hopefully, we'll make deliberate decisions as a society to move towards and embrace all the virtues that 5G can bring in. Right. That's all I had. Thank you for everyone.
Thanks,
If there are any
Sundar.
questions,
Thanks, Sundar.
happy to answer. If not, thanks for your time.
Great job, Sundar. Thank you.
Thank you.
Bye.
Appreciate it.